Welcome to this short tutorial about the law of decay. Today in this video I'm going to show you what the law of decay is, how you can calculate it with different equations, and what equations can be derived from this simple equation that you already see here on the screen, and what other laws are also dependent on the law of decay. So first things first, what is the law of decay? The law of decay is a physical law described in mathematical manners that describes the possibility and properties of a nuclear core of an atom to be in a state of decayment, so giving up, for example, an alpha particle, which is just a helium core of the helium atom. So that's the law of decay. So it's just a mathematical law that describes the amount of cores that are decayed over a certain amount of time. So I said, how can you calculate the law of decay? Because it's a mathematical but also physical law. We also have a lot of math coming up. So let's start with this. N of t. N of t is the amount of cores. N stands for the cores, or the amount of cores, and t for the time, which is also found back here in the equation. The cores to the given time, the amount of cores that are still remaining to the given time, and 0 are the cores where the t equals 0. So time equals 0, which then results in n0 having the base amount. 1/2 is because of a certain property of the law of decay. The law of decay has statistical properties because it is dependent on one simple fact. It calculates how long it takes, or how much time it takes for the base amount n0 to become half of its predecessor, and the time it needs to become the half is known as t1/2. That's also the thing that you would write in any equation that would need t1/2. So that's like a factor which you multiply this by, and then how many times do you multiply this factor with n0? This is certainly here. T is, like I said before, the already past time, and t1/2 is the time that one sort of atoms, one kind of atoms, to be halved in their mass. Not the core itself is halved, but the amount of cores is halved. That's a very important property. You may never forget that. So that's certainly simple, isn't it? Why don't we come to something more interesting, like B? What I'm writing I can still explain. So what I'm writing here is that B, which is the percentage of the amount of cores that are still remaining to the given point t. This step here is important to see, which we will see in a second, because I've also said what equations can be derived from this. At the end I'm going to give you an example which you may calculate or not, but you now have an idea how to calculate it. So as you can see, if we with this equation do this, we then get what is called B. So B also equals 1/2 t divided to the power of t divided by t 1/2. So that's the equation that you get from B. In which way does this help us? Well, it's easy to get nt because it's already the base equation is already at nt, and n0 is also not that hard to get. You just need to divide it by n0 and then do divided by nt and then swap the whole thing. It's also not that hard. I'm going to show you in a second if you want to, or I'm going to show you at the end. But for things like t and t 1/2, it's better if you put nt and n0 together to one bigger value. So in this case, I'm going to show you how to calculate t and t 1/2, and then I'm going to show you how to calculate n1 and 0. So what we have to do here is do the following. We do times 1 to the power of t 1/2 divided by t. Why do we do this? Of course, this would give us here the possibility of t 1/2 and here t, which would then cancel out both. And here on the other side, we'd have this. So we put them on the other side. In which way does this help us? Well, with a logarithm of 1/2 to the base of b would equal to t 1/2 and t. This brings us a step closer because we now have this exponent down to non-exponent. So what we can do pretty easily is just take times t, and then we'd have times t over here, and we just grab this t 1/2 stands alone, and we have the possibility to get t 1/2. And another thing that we could do is instead, well, after this, that's better, we do divided by the logarithm b 1/2, which would then result in this being divided by the logarithm. I hope you can follow me through on this one. Just have to imagine this. It's hard writing with this, so please excuse this. Divided by this, I'm going to write this in a better manner. A second. There we go. Like I said, it's quite hard. So that's I think it's a bit better this way. So we do this. A logarithm. No, it's not a logarithm. The 10th logarithm. That's logarithm. And I hope you can read it. I hope you can follow me through on this. It's quite logical, so you should have no problem. And then this would equal t. So we got the equation for t. We got the equation for n of t. We got the equation for t 1/2, which is down here. This is t 1/2. And now we need the equation for n0. So quite simply, we just do, and I'm just going to write down this equation again so we have a better overview, times t divided by t 1/2. So, and then we just divide it by 1/2 to the power of t t1 half, and then I'm going to get something because I'm going to need something. There we go. Sorry for this short manner. Okay, there we go. And now I'm going to take a new brush and another color. Scratch this so it's more clearly. Sorry it takes a while, but you get the point. And that's the main reason for me making this video, isn't it? And then we have n of t divided by 1/2 to the power of t t1/2 equals n0. And that's it. That's all the equations you need. And I said in the beginning, in the meantime, I'm going to scrap all the things we've already written down. In the beginning said there are some things that are dependent of this law, and one of those dependency is the calculation of activity of a nuclear active element of the periodic table. So we just go over here and now we write down the equation, which is not very surprising. T equals A, by the way, stands for activity. A0 T divided by T1/2. So this is the equation, and the equation is like the other one, but it's dependent of the other one because it's the same equation. Logical, isn't it? Or it may not be, but for me it sounds logical because it's the same equation. It's quite dependent. Well, it is the same equation, and when you think about it, it's logical because the less cores you have, the less possibility you have for a core to emit a amount of radiation, and with this being decayed. So, and in the very end, I'm going to give you a short exercise. I'm going to give you some so you can train this. There are also a lot of things on the web, so just search for the Law of Decay, or in whichever language this may sound too familiar to you. And we have t to be equaling 12 days. We have nt, which equals 30 cores, and we have n0, which equals 800 cores. So, if you want, send me the answer into the commentaries, and if it's and I may put, or I maybe put the right answer later in my description, or send it as a comment, and then you will be able to look it up. Or otherwise, if I forget it, don't worry. There are a lot of other better exercises than this, and it's a lot more fun to do this because the right solution is always on hand. So, thank you guys all for watching, and see you in the next one. Goodbye.